Hello, friends. This is Jim here, Science Talk. And I thought I'd do a video talking about human population and carrying capacity. Now, I've done some videos in the past with discussing resources and what the effects of humans are having on the environment. And I have stated my position that situation is not sustainable, that there are too many people on the planet for the available resources. We have a finite planet, finite resources, and putting more and more pressure on the land, putting more and more stress on the land. We're asking the land to do more and more for which it cannot possibly do. We need land for housing. We need land to grow, raise food. We need land to conduct business. We need land to extract resources, raw resources. It's not sustainable. Now, I actually made the statement that, and I'll explain this a little later on, that the carrying capacity for humans is about 100 million. And I've got some criticism for stating that, for saying it was way too low and that humans are smarter than that, etc. And it's like, it still comes down to the point that there's only so much resources to go around. Even if you got involved in a massive recycling regime, it takes energy to do recycling. I mean, I'm in favor of recycling as opposed to extracting raw resources because it also takes energy to extract raw resources. But we need to not look at this with rosy glasses, but keep it real. So I'm going to first discuss carrying capacity. So what's the definition? The definition is the number of individuals of a species that an ecosystem can support based on available resources, and this is the key phrase right here, that can be sustained and replenished. It cannot be sustained and replenished. You are going to outstrip the resources, and then the population crashes. Carrying capacity is usually designated by capital K or capital C. So, number of individuals of a species that an ecosystem can support based on available resources that can be sustained, replenished, renewed. Insert your synonym there. Now, I thought I'd throw in a couple of basic growth models. On the vertical axis, we see the population size denoted as N, and going up in increments of 500. So you have 500, 1,000, 1,500, 2,000. And they denote that K, this is just an arbitrary example, K equals 1,500. So 1,500 would be the carrying capacity. In the blue growth model, it's an exponential growth model, and we see dn over dt equals 1.0 n. Okay, in English, that means the rate of change in the numbers with respect to the rate of change in time is equal to 1 times n. This is a derivative. This gives you an instantaneous rate of change, the rate of change of n with respect to the rate of change in time. Okay. This is called a differential equation. This is also a differential equation. This is a logistic growth curve. So same thing. The rate of change in n with respect to the rate of change in time is equal to 1 times n times this 1,500 minus n over 1,500. This is a logistic growth. You notice how the logistic growth will flatten out. Exponential growth just keeps pulling several g's going up. Number of generations represents time. So these are some typical growth models. There are more, but that's all I'm going to touch upon in this presentation. To solve the equation, both of these, by the way, this is also a differential equation. A little more complicated, but still, it's solvable. To solve the equation in the previous slides requires using techniques used to solve differential equations. I'm not going to bore you. I'm not going to write out, I didn't write out all the steps and splat it on there. I'm just going to basically state what they are. So for the exponential one, n is equal to k times e raised to the rt. Okay? T is time, r is whatever the growth rate is. Okay? Now, the general form, they substituted 1,500 for k based on the previous slide. So it'll be 1,500 e to the rt. Now, I prefer to use n sub 0. N sub 0 is initial population. What this means is this is the population at time t equals 0, initial population. So I prefer to state that way. So instead of putting a 1500 here, general term, I'll have n is equal to n sub 0 times e to the rt. I'm using k to be consistent with how they were presenting it. Now, n will increase without bounds as time continues. Is this realistic? No. Eventually, the resources become limiting and n must decrease. This type of model is used as a starting point in population dynamic analyses, or when you're first learning about this in population dynamic classes. And even bacteria. Bacteria may show exponential growth, but even they run out of space and food and so forth. So the logistic, the solution is n is equal to k divided by 1 plus a times e raised to the minus kt, where a equals k minus n sub 0 divided by n sub 0. N sub 0 is the population time t equals 0, or the initial population. The t being in the denominator supplies us with the limiting value. That is the asymptotic value that the population will approach. In other words, the carrying capacity. This is more realistic model for population dynamics. So when you see, to the minus kt, as t goes to infinity, the whole term approaches a limiting value of k. Because what happens is this term will go to 0, leaving you with k over 1. That's what happens. That's what's going on there. So that's an asymptotic value. Asymptote is a value that a function approaches but does not intersect, generally speaking. So let's go back to those two types of curves that I showed you in the previous. The first one here is the exponential growth. Dashed line, horizontal dashed line represents the carrying capacity, population size, time, generation, and this is called the sigmoidal or logistic growth curve. Is also called the sigmoidal or S curve. So you have the J curve, because it looks like the letter J, and the S curve. The maximum number of individuals of a species that an ecosystem can continually supply resources to. Continually supply. Okay. That's the carrying capacity. Now, if we looked at bacterial growth curve, okay, you have a lag phase, which is got all these resources here, and it takes a while for them to their numbers are steady for a bit, then they start reproducing like mad because they're using up all this abundant resources. So then you have a exponential growth phase, and it may stabilize, stationary phase, and then as you use up the resources, it drops off, called the depth logarithmic decline phase. So the death phase is cell death exceeds cell growth. Stationary phase, cell growth is equal to cell death. Now, when we talk about cell growth, we're not talking about necessarily the size of the cells, but simply talking about the number of cells. Okay? And the log phase, the exponential growth with constant generation time. So this is what you see as they use up the resources, they die off. Now, I put in this here because the S curve is really two curves in one. The first section, we see growth rate increasing to about where I'm moving the cursor there. And I'll just put it right there. That's called the inflection point. More on that in a moment. The first section, lag and increasing growth, is exponential. The second section is a decreasing growth rate leading to the stationary phase is logarithmic. So when you see this portion here, that follows more of a logarithmic curve. This is following an exponential curve. That's following a logarithmic curve. The switchover occurs at the inflection point, which is right here. Now, the inflection point in calculus is a point, assuming it's continuity on the curve, is the point where the concavity of the curve changes from concave up to concave down, or vice versa, concave down to concave up. Now, if think of this as a salad bowl, will it hold the salad or will the salad dump out? Concave up will hold the salad, concave down, salad's on the floor. But so this is the inflection point where it changes over from increasing to decreasing, or concave up to concave down. And this is just another way of showing it. Peak population refers to carrying capacity. Transition from increasing growth, decreasing growth is called the inflection point. Population increase at first due to abundant resources. Then the growth rates decrease because resources become limiting. But this is what's actually going on. There's an oscillatory situation that goes on. It seems like the theme for my videos lately is oscillations, isn't it? But hey, that's, nothing is static in nature. So what actually happens is the population numbers oscillate around K. If they overshoot, like we see here, okay, corrective measures bring the numbers down, usually below the carrying capacity. Then the resources replenish, renew, okay, followed by a population increase to take advantage of the newly available resources. Then they overshoot again to be corrected again, etc., etc. This is an example of a negative feedback loop. Negative feedback loops does not mean bad. It simply means corrective in nature. Positive feedback loop is where you get into runaway systems. Like, warm up the atmosphere, thaw out the permafrost, release more methane. Methane warms the atmosphere more, thaws out more permafrost, releases more methane, etc., etc. That's a positive feedback loop. It's a runaway system. Negative feedback loops are corrective, so that you oscillate or tend to some sort of preferred value or preferred situation, or ideal, if you want to use that word. Your body, in maintaining homeostasis, is always engaging in negative feedback loops to keep your body happy. Now that we have an idea what carrying capacity is and the growth curves and etc., let's now examine human populations. So this is showing Old Stone Age, Agricultural Revolution. We have New Stone Age, Bronze Age, Iron Age, the Middle Ages, then modern times. This vertical dashed line indicates the start of the Industrial Revolution. I'm going to have to say something about that in a moment. As you can see, so this scale is in billions, 1, 2, 3, 4, 5, 6 billion. So as you can see, human population for a long time was wallowing down here, maybe a couple 100 million and so on. It's kind of steady, kind of in balance. Started increasing a little bit, and you can see the big drop off due to the plague. Here's the Industrial Revolution, and then look what happens right after the Industrial Revolution. Boing! It just shoots up. There's another reason for that, but the Industrial Revolution made possible, along with the other fact I'll mention briefly momentarily, this huge spike in human numbers. This is not sustainable. Human population growth from AD 1 to 2013. This is about 250 million folks, about AD 1. We hit 1 billion people in 1800, 2 billion in 1927. Okay, so to double took more than a century, 123 years. To increase, now let's look at from 2 to 4 billion. That's another doubling. That's 47 years. So you go from 123 years to double the first billion, and then to go from 2 to 4 billion, less than a half a century, 47 years. And we're on our way to 8 billion. We're, 2009, we're about 7.5, 7.6 7.7, somewhere around there right now. So we're almost at, so let's say we hit 8 billion, projections are we'll hit 8 billion like by 2025 or 2030 at the latest. So therefore, that's now what, another 50 years or so to keep doubling like this. This is insane. Here's some of the projections. By the time we get to 2040, okay, would be over 9 billion. But look at this spike here, right? That's just not sustainable. And this is a projection based on median fertility estimates, and the source is the UN Population Division World Population Prospects, published in 2014. So now this takes us back, the furthest slide didn't go back as far back as 10,000 BC. And as you can see, we're sitting about 100 million folks planet-wide. Start doing plowing and irrigation, so more the agricultural, agrarian societies onset. Numbers start to increase, but they're still kind of maintaining this level. Goes up a bit of a die down. Here we have the bubonic plague, and then once again, right there, the Industrial Revolution begins, and whammo. It is no surprise that the population skyrockets with the onset of the Industrial Revolution, as does the levels of CO2 in the atmosphere. Coincidence? No. This is an amazing statistics right here. This is 2006. This is 13 years ago. The number of people increasing on the planet per day was 211,000. Now, here's the other fact. In addition to the Industrial Revolution, another major factor contributing to explosive human growth is germ theory and modern medicine. Once the germ theory came about, we understood about diseases and infections and that kind of stuff, and then ways to start to treat them. That led to modern medicine. And you will note, okay, 1959. So here's World War II, right about in here. Okay, World War II did not reduce the population significantly because World War II were already over 2 billion. And basically, there was like an estimated, what was it, 20 million people, 25 million people, however many died in World War II. Might even be like, even you want to say 50 million. Okay, if we're at 2.5, we're at 2.5 billion here. Okay, 250 million would be 1/10. So 25 million is 1/100. So even if you had 50 million people died, it's 1/50th. That didn't put it, as horrible as it was, and all those people dying, etc. is horrible. It didn't significantly impact the number of people. Now, here's the other interesting thing here. Okay, it's hard the cursor disappear. All right, from 2 to 3 billion took 37 years. From 3 to 4, 15 years. 4 to 5, 13 years. 5 to 6, 12 years. 6 to 7, 11 years. We just keep, and the projection is 8, 7, 5, 4, 3, 2.5 years to get up to eventually 13 billion. Okay, now they're saying 8 to 13 billion people by year to 2039. I would go with the lower estimate. I would say it's probably more like around 8.5, 9. Projections I've seen are predicting 11 by 2050. That's the projections I see. So you might want to take this curve here and just flatten it a little bit this way, kind of slow the rate down a tad. But still, whatever the numbers are, it's just too many. Earth cannot handle all of this. In 2006, 211,000 people per day were added to the world. It's much higher now, obviously. Okay. World population growth, 10,000 before current era to the present. This is a log scale. So log scale helps, linearize or shrink down the spacing so it's a little more readable. We have the semi-nomadic era, early agriculture, copper wheel, the era of the city-states. We start getting to the agrarian society, Bronze Iron Age, the era of empires and epidemics. Then we have the global era, translation referring to industrial revolution. 100 million. That's that number you've heard me talk about. I'm going to be talking about that more so. So we reached 100 million at about zero, the year zero. A little before that, but let's say around there. So all the people have been adding extra stress to the planet. Now this is 700 million. So 700 million is 7 billion. I just divide by 1,000. That's the number of billion. But they're doing that deliberately. 1 million, 4 million, 10 million, 40 million, 100 million, 1,000 million, which is 1 billion, 2 billion, 7 billion. So you can see get another look at this growth scale. This is an interesting one. Looking at from 1950 projecting out to 2100. Okay, 1950, 2.5 billion. Okay, about 2015 or so, 7.3 billion. Here's 2020. So that's approaching 8 billion. Okay, but notice what's happening. The line, the curve is starting to flatten. It would seem to imply, oh, we're approaching a carrying capacity. Well, what's going to happen? They didn't extend this, but if they'll do realistically, we'll probably do that. We'll probably just dive off like I showed you earlier in that bacteria slide, right? I suspect that sooner or later, this is the growth curve for humans. It's going to smack right. It's going to dive right down. Has to. So what is this graph here? Okay, got 13.3 billion here, 9.5 billion here, the green. 11.2 is what's called the median, kind of like the center location between these two extremes. Now these are all predictions. This is all based on modeling. So the tan, I guess it calls the upper 95%. The green is the lower 95%, with the red being the median. So basically there are some folks are saying that it's not going to continue exponentially, or if it does, it's going to slow down its exponential rate. E to the RT, the R will become a lesser value, is what they're basically saying. Some other people will say that this will start becoming logistic and perhaps followed by a die-off. I don't know. Now, this is a little something I put together just to kind of model what the problem is. So on the vertical axis, we have n. N is the number of whatever. It could be the number of people or the amount of a resource. So this curve that you see decreasing represents available resources. This curve here that you see increasing represents human population. Where they intersect is the equilibrium point. Think of that as your carrying capacity. Now, to the left of the equilibrium point, the resource curve is the upper curve. The human population curve is the lower curve. So that means the amount of resources is more than the human. So you can also think of this as, the demand for the resources. What, available resources, demand for it. So this is telling us that since there's more resources than humans are demanding, things are going to be fine. You're not going to run out of resources. But on the other side of the equilibrium point, we now see that the human population curve is the upper curve and the resources becomes the lower curve. Now the demand for the resources is going to be outstripping what is available. And eventually, the resource depletes. It goes right to zero. You run out of resources. And then what's going to happen after that? Well, you're going to have mass correction in the human number, in the human numbers of humans. Mass correction. So the median is the human population growth is exponential at the moment, and the resources are not able to be replenished. Not able to be replenished. Remember, carrying capacity, you have to be able to replenish the resources so you can sustain that population. This is an artificial construct, and it's not sustainable. Land is being destroyed to obtain minerals and trees, etc. Whatever raw resources people are going after. This is happening without renewal, aside from some tree planting program. But when mining minerals, the land is destroyed. Okay, I'm guilty of it too because I'm using a thing called a laptop. If you have a computer, laptop, desktop, what have you, you have a tablet, you have a cell phone. Okay, they have to mine raw minerals to put together that device, which is also energy. Uses a lot of energy because of the mining equipment, the heavy equipment to get out there and tear up the land to obtain those material. So there's more and more, and of course they design laptops. As I found out recently with my laptop, kind of shit in the bed because the motherboard went belly up. They make laptops to last 2-3 years. That's it. And it goes to obsolescence very quickly. Yeah, you can recycle some of the stuff, but you have to keep mining to get, to build more laptops, build more cell phones, smartphones, what have you. So as human numbers increase, more pressure is placed on the land. Land is needed to house people, grow, raise food, conduct business, obtain raw resources. The amount of usable land is finite, as is the amount of resources is finite, and available land is decreasing. With increasing human population, decreasing available land, the two curves will not intersect. Well, once you pass this point here, they'll never intersect. So you can think of this as like this being back towards like 10,000 BCE or something like that. And this might be, say, like around, the year zero. Okay. But now, what's the old saying? The ship has sailed. This is not sustainable. It's not going to intersect. But that was just a little hiccup when I was drawing the line. Nothing significant there. So amount of usable land is finite, available land is decreasing with increasing human population, decreasing available land. The two curves will not intersect, nor will all needs be met. This is why this is not sustainable. This is why many population ecologists place the carrying capacity from humans from about 200 million to 600, from 20 million to 650 million. Okay, 2 times 10 to the 7. So that's 20 million to 650 million, with a median value of approximately 100 million. So this is like overly optimistic. This is overly pessimistic. This is the median. Okay. Now, if you want to argue that the value is 250 million, 300 million, okay, you can make those arguments, present them. That's fine. But the point is, humans have 7.5 billion now, maybe even closer to 8 billion, and increasing still. Human population cannot continue to increase. Sooner or later, corrective measures will happen, be it pestilence, pandemic, mass starvation, wars. And do not forget, clean water is becoming scarcer and scarcer. This alone, lack of access to clean water, will result in high death rates. Right? Look what's happening in Flint, Michigan, where a lot of communities across the U.S. where there's lead in the water. There's a whole bunch of crap. I just saw something, came across the Twitter feed that, I forget where it was, I think it's like Virginia or something. I forget where it was. You open up the tap and purple water is coming out. Like, what the hell is that? And they're saying, oh, it's safe to drink. That looks like potassium permanganate solution. I ain't drinking that stuff. But this is what's going on. And that's why I think it's going to be fought over access to clean water. Sooner or later, human population will crash. Anyone who thinks this can continue, this human growth can continue unabated, or that technology will save the day, is quite frankly deluding themselves. As human density increases, with people becoming more and more crowded, humans will turn on each other, creating conflicts. Humans will act very similar to what happens when you place too many mice in an enclosure. They eat each other. Humans will attack each other, fighting over ever dwindling resources. Remember, humans are still animals. And this was a sign that was in the research institute that I worked at. I have this on a sweatshirt. A good planet is hard to find. And we're just pissing in our bed, shitting in our bed, and we're just ruining our only home. But again, I cannot stress enough, with just more and more people on a finite resources, finite land, it's not sustainable. Something will give. You're not going to be able to grow enough food to feed all the people. You're not going to be able to get enough land to house all the people. It just cannot continue. So I mentioned that the range is from 20 million to 650 million, with a median value of approximately 100 million. So basically, the size of the human population before the year zero, was the carrying capacity. If you look at the median value, I showed you this chart showing the median value. So what is the median? Okay, the median is a central value of a distribution. That means that half of the data, 50%, is found less than the median value, and the other half is found greater than the median value. Median is thus referred to as the 50th percentile. Mean is the mathematical average. Sum up the values, divide by the number of items summed up, and that number is the mean or average. But means can be skewed, that is, biased in a direction. Median is a better measure of central tendency. Now, if you have a perfect normal distribution, then the mean and median will correspond to the exact same value. So what I've done is to illustrate what I just stated above here is some incomes from a generic community, and I listed them in increasing value. So we're starting from 28,000, going up to 41,000, then 280,600 bucks. There are 20 entries. I got 3, 6, 9. There are 10 per line. The median will be found between the 10th and 11th entry, between 36.9 and 37.2. Do a quick midpoint of the two of them is 37,050. Now, add up these 20 values, divide by 20, the mean or average is 47,652.20. You see how it got skewed? This one value skewed significantly. To summarize this example, the median is 3750, the mean is 47,652. The difference is about 10,600, which is a definite skewing. So now why am I mentioning it? Okay, and I mentioned when I talked here the median value of approximately 100 million. When looking through various papers discussing human carrying capacity, jot down the numbers that these papers were assessing or arriving at. 100 million was the median value of those papers, basically. So 100 million, we're at 7.5 billion now. That means we are at 75 times above the carrying capacity if we look at the median value. If it's closer to 8 billion, it's going to be 80 times above. Now you can say, okay, look at the upper end, 650 million. It's not so bad. It's still an order of magnitude. Above the carrying capacity. Still not sustainable. So I want to show you, give you a quick little example of the difference between median and mean. Now, if you folks would like for me to go take this topic into further depth to discuss, for example, the first and third quartiles, the interquartile range, how to determine if a value is an outlier, talk about the normal distribution. If you would like for me to do that, let me know in the comments section, and I'll happily put together such a video. I put together a couple of videos some time ago where I gave a general intro to stat, and I did a general intro to a linear regression. So you might want to look for those, but I will happily put together a video discussing tendencies and values of measures of spread and so forth. And that includes standard deviation. I'll look at the normal curve, what's meant by plus or minus 1 standard deviation, plus or minus 2 standard deviation, and so forth. So if you like for me to put together such a video, let me know in the comment section and I'll get to it. But I wanted to do this video to explain to you, share with you what's meant by the carrying capacity, how it works, what's it all about, and then relate this to humans. And I hope I've been able to show you that the number of people we have, you're looking at the available land, available resources, is not sustainable. Human growth cannot continue in a J-curve exponential manner unabated. There has to be a massive correction, and it's going to be an ugly crash, but it is coming. Basic ecological principles instruct us so. And just look at that little graph that I made, this little model here. So thank you for your time, and we'll talk soon. And remember, a good planet is hard to find. Hey folks, this is Jim here reminding you to please subscribe to my channel and please share my videos with others. Also remember to click the bell so that you know when I drop in a new video. I also ask that you please consider becoming a patron of my channel and support the work that I do by going to patreon.com/Science Talk with Jim Massa, each word separated by an underscore, and becoming a patron. It's asking for as little as $3 a month, cost of a cup of coffee, to support the work I do and keep my informative videos coming your way. Thank you for your support.